So 4.7 introduces the idea of the normal force. We've actually been talking about the normal force for a while, but it's actually talking a little bit about the mechanism. And the thing to really keep in mind here is that the term normal really means perpendicular to the surface. All right. It's easy to get confused and think normal as opposed to normal versus abnormal, but it has nothing to do with that. It has to do with the mathematical idea of normal, which is just something that is perpendicular at right angles to a surface. So we see here, this is kind of how the normal force comes about. If we look at our ball and spring model, you put something heavy down, that's going to cause all these springs to stretch now and compress. As they compress and stretch, they're going to exert a force back towards their equilibrium position, and that is the normal force. So this normal force is always at right angles to the surface. So if we have a brick that we're pressing up against a wall, then the normal force is at right angles to that surface. It's pushing it back away. Now, a lot of times there's also a frictional force involved. And well, it's true that, say that we're pushing on the brick to the side. Well, it's true that the table is applying both the normal force and the frictional force, so you could say the force on the brick by the table was pushing back and up. But the convention is to split it into two forces, and the reason is because we need to use the normal force to actually calculate the frictional force. So when you draw your free body diagram, always separate the frictional force from the normal force. Now, the two forces are always at right angles to one another. Just like the normal force is always perpendicular to the surface, the frictional force is always going to be parallel to the surface. So keep that in mind, that these two forces are operating in 90 degrees to one another. So here we have the equation for the static force. And it's only a scalar equation. It doesn't have any direction associated with it. This is one instance where you are actually going to have to determine the direction of the vector. So you actually have to look at the problem and figure out, okay, which way is this frictional force, and then write this in terms of a vector once you've calculated the magnitude. So notice here that we have this less than or equals to sign in the force. And that's because this value right here is actually the maximum value the static friction can have. Once you exceed that value, the object is going to start sliding and moving. You'll have to deal with kinetic friction. But as long as you are less than that value, static friction is still in effect. So this calculation only tells you the maximum. If you're pushing, if this applied force is less than that maximum value, this equation doesn't tell you the magnitude of the frictional force. What you'll have to do is use the fact that the net force is 0 if this thing is not changing velocity, and use that to calculate what the static friction force is. All right, I want to reiterate that point one more time. This equation only helps you find the maximum static friction force. In most cases, to calculate the static friction force, you're going to have to use the fact that usually the net forces are 0. So in this case right here, if there's an applied force, and if the applied force is less than this maximum value, then from my free body diagram, we have F applied in that way, and we have F in that direction. Since this thing is not changing velocity, not changing momentum, the net force in that direction has to be 0. So F plus F applied is equal to 0, 0, 0. In other words, F is equal to the negative of F applied. Okay, so this is how you're going to have to find static friction most of the time. Now, once it starts moving, then we have kinetic friction, and the kinetic friction is roughly constant. When you start to get up to high speeds, there can be some speed dependence, or if the surfaces are somehow strange. But for most situations, this is a valid assumption. And for the purposes of this course, we're just going to go with this as the the magnitude of the kinetic friction. Now, this frictional force is always going to oppose surfaces from sliding. You want to be careful because you sometimes get in the mindset that friction opposes motion, but you have to say motion of what with respect to what. So in this case here, you're pushing on the block, trying to move it to the right. So in that case, it's pretty clear that the frictional force is trying to oppose you in the direction that you're moving. But let's look at a little bit more complicated situation. Let's say that we have a box in the back of a truck, and this truck is speeding up in this direction. In other words, its delta P is to the left. So the question is, which way is the frictional force on the package by the truck, assuming the package doesn't slip? Well, if there was no friction, this package would stay in place as the truck moved. And so these two surfaces would try to move in opposite directions. This top surface here would try to move that way. This surface would try to move that way. So the frictional force on the package is going to oppose that slippage. So what that means is the static friction force on the package by the truck is in the forward direction. Another way to think of it is, if it's not slipping on the back of the truck, it has a delta P in the same direction. Its momentum is changing to the left as well. The only way that delta P can be in that direction is if there's a net force to the left. What's applying that net force? Well, really the only force in the horizontal direction that makes any sense is the static friction. Now, if we go ahead and look at the frictional force on the truck by the package, well, we can think of this two ways. First off, that's going to be the third law pair to this force right here. So this is the F static on package by truck. We know just by the third law that the static friction on the truck by the package would be in the opposite direction. But another way to look at it is in terms of the slippage of the two surfaces. This surface wants to slip this way. This surface wants to slip that way. The frictional force is going to oppose that. So F static on truck by package is going to be in that direction to oppose that slippage. So keep those ideas in mind when you're calculating the frictional force, and hopefully that will help you out.